How's the party? Yeah, good? Good? Yeah? I'm impressed at how many people are here after the party, actually. And how many people are here on the last day? So thank you for coming. Thank you for staying for Ignite. How many people are here because you want to learn how to get rich fast? Okay, not that many. Good. Well, so my name is Mark Russinovich. I'm going to, this morning, give you an introduction to blockchain. And to set the context for blockchain, I'm going to start with the roots of where blockchain came from, which is a cryptocurrency that I'm sure everybody in the room has heard of called Bitcoin. So I'll start by talking a little bit about Bitcoin, then I'll go into the foundations of Bitcoin, which set the stage for understanding blockchain that requires a little bit of cryptography. So I'm going to cover some cryptographic basics. Some of you might be familiar with these cryptographic basics. Some of you might be familiar with the terms, but not exactly how they work. So I'll be going through those briefly. And then I'm going to get to the meat of blockchain. What are transactions? What are transaction chains? What are blocks? Then I'll get into smart contracts and consortium blockchains, which is where business comes into play. And then I'll talk a little bit at the end about what Microsoft is doing with blockchain. So let's go ahead and get started. I'm sure everybody in the room, like I said, is familiar with Bitcoin. And Bitcoin mania really kicked in at the end of last year. The Bitcoin prices were going crazy. And I'm sure all your friends and family started to talk about Bitcoin. I had friends who have sons and children that basically were like, I'm quitting college. I've learned how to make money. I'm using cryptocurrency, Dad. And I'm getting rich, and I'll never have to work again. Well, they're back in school now. How many people have lost money on Bitcoin because you bought into the mania? Okay, I can tell you're not willing to admit it at this point. But this caused this fear of missing out, all these stories about people getting rich. And this mania even transferred into the business world, where you had companies like Long Island Iced Tea changing its name, pivoting away from iced tea. It's doing a decent job at iced tea, but they said, we can do better with blockchain. And so they changed their name to Long Blockchain, and their stock price went up 200% the next day. So this is the kind of craziness that we were seeing. And here you can see back in December, that big spike. This is the Bitcoin's current price. You can see it's come down. So it's above where it was about a year ago, but still far from the heights that it achieved. And now there's a whole bunch of people that are saying that Bitcoin's hype is gone. We're here to stay in the lowlands. There's people even that are saying that Bitcoin is a bunch of nonsense. Like Warren Buffett, this is an expression I didn't ever expect to hear out of Warren Buffett, which is Bitcoin is probably rat poison squared. And the ironic thing about this is there's a cryptocurrency called Ratcoin. Its price doubled the next day because of this. My own tale of woe. About a year ago, 2 years ago actually, I decided to experiment with cryptocurrency. I didn't know anything about it, but I wanted to learn about blockchain and cryptocurrency. And so I placed modest investments in Bitcoin and another cryptocurrency called Ethereum I'll talk about later, $50 in each. This was in July. It actually had reached over $5,000. My $50 had translated into $5,000 last December. Here's where it was in July. Ethereum didn't crash quite as hard as Bitcoin then, but I checked this morning, and here it is. So I can't even buy an iPhone XS now with this. So where did Bitcoin come from? You might have heard of a person named Satoshi Nakamoto. It's a very elusive figure. Nobody knows exactly who this is, or even if it's a real single person or an organization. There's all sorts of conspiracy theories. But because this paper was published under this name, but nobody's ever been identified as this person, as much as the whole world has been trying furiously to figure it out. And there's various people that come forward and say, I am Satoshi Nakamoto. Well, the thing is, I'll come to it. There's one easy way to prove that you're Satoshi Nakamoto. Nobody's done that, and I'll come to that in a minute. But this paper laid out the fundamentals of blockchain in the purpose of serving this cryptocurrency called Bitcoin. It is, I recommend, a very good read to get the fundamentals. I'm going to be quickly going through what's in that paper, but if you just want like a 4-page read on, 5-page read on what is the foundation of all this mania, that paper is a great, very simple, easy read on understanding those basics. And the reason that it's very easy to prove who Satoshi Nakamoto is that when the Bitcoin cryptocurrency launched, the initial transaction deposited a bunch of Bitcoin into Satoshi's account. Some of it's been spent, but there's about 1 million Bitcoin left in that account. And anybody that wants to prove they're Satoshi, all they have to do is submit a transaction from that account to the Bitcoin blockchain, and that proves that they have access to that account, which only Satoshi Nakamoto should have access to. This 1 million Bitcoin obviously is a huge amount of money, so whoever this is or whatever organization it is, at one point in time, you can see that this person would have been the 44th richest person in the world. Tens of billions of dollars of net worth based off of that Bitcoin has come down, of course. Now, cryptocurrency I've been talking about in the context of Bitcoin, and why is cryptocurrency so interesting to people? To understand that, you need to understand what fiat currency is and compare that to what cryptocurrency is, because they're very different. With fiat currency, it's issued by governments. It's like the US dollar. The government prints the money and stands behind that money. And what this causes is there's delays in settlement when one party wants to pay another party some money, especially when you're going across international borders, because then you're going from one fiat currency to another fiat currency typically, or one banking institution to another one, and that means that there's settlement times that have to be put in place to make sure that neither party is screwed out of their money as this thing is in transit, which is why when you do a wire transfer, it's usually 2 or 3 days before that wire transfer clears. There's also, in many of these situations, even a need for an intermediary to protect both parties, where they can sit and hold the money kind of in this intermediate state, where if one party defaults, the other party's protected. And so even the international banking systems have organizations that sit there as intermediaries for those cross-border payments, which make them take even longer and add a lot of cost overhead to the transactions that go cross-border. There's also high transaction fees, usually associated with all of this friction that's caused by these intermediaries in the middle and the risks of these payments going from one party to another. So cryptocurrency aims at addressing all of these. One of the key aspects of cryptocurrency is that it's decentralized, meaning that there's no single organization responsible for managing it. It is an autonomous system that's operated by a whole network, a network of parties that don't have to trust each other to participate in that network. There's no clearing involved. When one party sends Bitcoin to another party on the network, it's effectively instantaneous. I'll talk about it's not quite instantaneous, but when that transaction is executed and accepted by the network, then everybody sees that as the ground truth. There's no intermediaries. Like I said, you can just submit a transaction to the network directly and send money to another party or any other parties without having to go through these intermediaries that are going to sit there and protect each other, because there's no need for that protection. And one of the spin-off aspects of this, and one of the requirements to make this trusted, decentralized system, is that there's an immutable history of the transactions. When I pay somebody in Bitcoin, what goes into the Bitcoin network is a log of that transaction, and nobody can tamper with that log without it being visible that somebody tampered with it. There's a way for somebody to go verify the authenticity of that transaction chain log, and I'll show you how that's done in a minute. So that cryptocurrency is built on top of blockchain, which gives it all these properties. Blockchains are also called distributed ledger technology, and blockchains get their fundamental properties that give cryptocurrency those properties from cryptography. So I'm going to talk a little bit about the cryptographic basics in a second, but I want to start out by asking this question: why blockchain? Because really, when there's a business looking at blockchain, and I'm going to talk more about business scenarios in a little bit, there's one question that you've got to ask up front, which is, why do you want to use blockchain for this? There's been so many companies that have come to us at Microsoft and said, hey, blockchain, what can I use it for? Or here's a problem, I want to use blockchain on it. Why? Because blockchain. So it's like a hammer looking for nails. And so you got to step back and say, why do you want to use blockchain? And the answer, the fundamental reason to use blockchain is that there's no that there's several parties that want to interact with each other, typically transact, send assets from one to another, and none of the parties trust each other to operate the database. And they don't even trust anybody else to operate the database on their behalf. Or they'd rather not, because that would introduce friction and cost. And so that effectively means that you've got a network of partially or fully untrusting participants that want to transact with one another directly. And none of them trust any of them to operate a database. So the benefits that blockchain give you, besides the ones that I've talked about, is that you can't censor on a blockchain. The network accepts transactions, and as long as some party is willing to accept a transaction, they can put it into the blockchain. So it's very hard to keep transactions out. In a centralized database case, it would be very easy for the party operating it to say, no, I'm not going to accept those transactions. It's capable of accommodating anonymity or pseudo-anonymity, meaning the parties don't have to be tied back to any real-world identities. They're represented with cryptographic keys, which are fairly anonymous. There's ways you can actually, looking at transactions, and if you've got some connection to a real world, you can de-anonymize a key, but effectively they're anonymous. They're resilient to failure because the whole network's maintaining the database, not a single organization, not a single server or network of servers. It's really everybody's got copies of it. And the immutability means that there's a verifiable audit log that you can validate a transaction based off of simply its transaction ID or its hash that I'll talk about. Now, the alternatives in many cases where somebody comes and says, hey, I want to use blockchain for this, are a centralized database. A trusted operator you want to outsource the database to, as the members of your party will transact with one another. Another option is trusted execution environments, or TEEs, which I'll talk about at the very end of the presentation, which are enclaves where if you trust the code in the enclave, you can trust that enclave, and you trust the enclave itself, like the hardware that it implements that enclave, then you can trust that running anywhere, even outside of your own network, even on somebody else's machine. And that might be a way to solve this problem without blockchain. And then multi-party cryptography. That's another potential solution to this, like using homomorphic encryption. So if you're interested in the anonymity aspects of blockchain, you can get that through other means. So I just wanted to set that up, and I'm going to come back to the end, and I want you to keep that in mind as I go through this presentation, is that blockchain's not the answer to everything. It's the answer to this very specific scenario. So let's talk about the cryptographic basics, starting with the hash, which is also known as a digest. This is a succinct representation of something very long, could be very long, like the Cliff's Notes for War and Peace, very succinct representation of the book War and Peace. And the key aspect of this is that Cliff's Notes, you'll never find two Cliff's Notes for different books that are the same. Every book resolves into a different Cliff's Notes summary. And it's impossible to go from the Cliff's Notes summary back to the book. If I give you the Cliff's Notes summary for War and Peace, it's impossible for you to go back and produce the whole book, War and Peace. That is a property called one-way hashing, which means that I can create the succinct representation, but I can't go from the succinct representation back to the original. In fact, I can derive basically no information about that original from the summary. Now, when it comes to digital hashing or summarization, you've got a cryptographic hash function. SHA-256 is the one commonly used. And that's where you take some input and you transform it through this hash function into a fixed length set of a binary. In the case of SHA-256, it's 32 bytes, or 32 bytes of binary. This is a more succinct form, but the property here is that if you change anything, you change one character, you're going to come up with completely different hashes. So hashes are a great way, and these functions are also what's called collision resistant. It's extremely hard or impossible to find, virtually impossible to find two different texts that will result in the same hash. So it's got this very kind of cool property, which seems counterintuitive. And that means that you can represent just about anything uniquely and verifiably just with its hash. And we'll be talking about hashes in the context of blockchain transaction IDs a little bit later. A second concept is encryption. I'm going to talk about the encryption that we're all familiar with, which is symmetric encryption. This is when you take an unencrypted message, you take it through a symmetric encryption algorithm, which has a key associated with it, a symmetric encryption key, and then you produce some garbage. And this garbage right here looks like what you see when you accidentally open a Word document in Notepad, right? Oh, come on, I know you've done it. I've done it. And then you can take that same key and go and decrypt it. So as long as you got the key, you can either encrypt or decrypt and get back to the original contents. Blockchains rely on a variant of this called public key cryptography or asymmetric cryptography, where there's a lock and two keys. And the property here is that the lock can be turned one way by one key and can only be turned the other way by the other key. That's the simple kind of way to think about this. So if I've got the green key or the public key, I can move from the unlocked position into this locked position on the left side. But I can't use the green key to go to the locked position on the right side. So the green key can only turn this direction counterclockwise. The red key or the private key can turn in the other direction. Now, the way we label these is a bit arbitrary. I just define one and say this is the private key, the other one's going to be the public key. And the idea here is that I can take a piece of text and then I can encrypt it with my public key, which means taking it from the locked position to the unlocked position with that public key. And then the private key can be used to go and decrypt it. So in this way, I can, with my public key, actually this is, I can encrypt something so that only the intended recipient can get it, at it. If somebody creates a key pair and they give their public key out to anybody, now anybody can take their public key, encrypt messages that only the person with the private key can see, because the public key cannot go the other way and decrypt that message. So that's one of the cool properties of this asymmetric encryption. So if you have an unencrypted message, you encrypt it with your public key, you take that encrypted message, you send it to the receiver, they can take their private key that corresponds to that public key and decrypt it. And that is a way to securely send messages such that only the receiving party, intended party, can get them. There's another use for public key cryptography, which isn't for sending messages that are encrypted, but for verifying that somebody has looked at a message and basically stamped their seal of approval on a message, or said, or given you evidence that they have seen that message. And that is a process called signing. With signing, you take the message and you encrypt it with your private key. And at that point, somebody with the public key can decrypt it. So this is the opposite. This is where I take my private key, I encrypt something, everybody has my public key, so I can hand it out to everybody, and you can all decrypt it with my public key. The only key that can decrypt it is my public key. So now you know that I'm the one that encrypted it. Nobody else could have encrypted it. And if I encrypted it, that might mean something like, I approve of this. So those, just playing this out, looks like this. I take a message. I send the message actually to you. I then hash the message. You hash the message. So we both have hashes. I sign my hash. So I encrypt the hash with my private key. Then I send you that encrypted message. You take my public key, you decrypt it, you get out the decrypted hash, and if that decrypted hash matches the hash that you produced of the plain text, then you know that actually I approved of that message. I signed that message. So that's signing with asymmetric cryptography. So now we've got basically the basics of cryptography. Let's talk about the blockchain basics now. So first, talking about transactions. I mentioned I want to send somebody some Bitcoin. So Bob wants to pay Alice 10 Bitcoin. What Bob does is creates a transaction, which that transaction has to refer to a previous transaction that had given Bob 10 Bitcoin. So this is like saying, I'm taking that 10 Bitcoin and I'm going to give it to Alice. Now, the way that Bob proves, or the way that Bob shows who he's giving it to, is to embed with that transaction Alice's public key. So this is basically telling the world, Alice is getting this. If anybody knows Alice's public key, they can see that it's Alice. Everybody else just sees that there's a key there, that whoever owns that key is entitled to this Bitcoin. And then what I do to show that I'm actually willing to give my 10 Bitcoin to Alice, as Bob, is that I sign that transaction. So I hash it, I encrypt it with my private key. And now anybody that gets my public key, and my public key's in there as well, so anybody can look at my public key and see that I'm the one that actually authorized this transfer of the 10 Bitcoin that I prove that I own to Alice. And so that's the basic of a Bitcoin transaction or any kind of cryptocurrency transaction. And then what this causes, if you recall, what I said is that that Bitcoin that I'm paying to Alice, I have to point back at previous transaction to show that I have got that Bitcoin, that that's the Bitcoin that I'm spending. And so what this creates is a chain of transactions over time where this Bitcoin transfers ownership as it's transferred. And so, well, let's see, right here, owner 0 signed this transaction giving Bitcoin to owner 1 and placing owner 1's public key there. Now, at this point, it's under owner 1's control. Owner 1 can take this Bitcoin and give it to somebody else by bringing out their private key, creating a transaction that authorizes payment to somebody else, and the chain continues. And then anybody can go and verify, like I said, that owner 1 really did authorize this transfer to owner 2, owner 2 did really authorize this to owner 3, and then the chain continues. And so this is a chain of transactions. Now, that's not the reason that blockchain gets its name. I'll talk about that in a minute. But what I want to show you very quickly here is an example of a real transaction in the Bitcoin blockchain. So this is one of the very popular Bitcoin Explorer tools. It's at blockchain.com. And if you go to data, you can see blocks, which I'll talk about in a minute. But I'm going to click on a block here. And you can see that this consists of transactions. And when I click on one of these transactions, let me pick a better one. When I click on one of these transactions, there's the hash of the transaction. You can see that it prints us some summary about the transaction header, and then it shows us who this Bitcoin went to. So there's Bitcoin right here. This is referencing some previous transaction, and then it's going out to these accounts. And these accounts then each get some of that transaction. So one of the things you can do is if I've got 10 Bitcoin in this previous transaction, I have to spend the whole thing when I reference that transaction that gave me 10 Bitcoin. And you might think, well, that's just a waste. If I've got to spend it all, how do I keep it? The answer to keeping it is that if I want to give Alice 5 of that, I simply make an output that gives Alice 5 and another output that gives me back 5 to my account. And so that way, I preserve my 5 Bitcoin, and then I can refer to that 5 Bitcoin in a subsequent transaction. So that's a quick look at a transaction. Now, one of the big challenges here, the fundamental challenges, is how do you get everybody to agree about the order of transactions, which is the fundamental property of a database is this happened before that. And the reason that you need that, especially in cryptocurrency, is that you don't want a situation where Bob has 1 million Bitcoin and he wants to buy a Van Gogh. And Bob takes that 1 million Bitcoin and sends it to Alice, who owns the Van Gogh, and then turns around and creates another transaction giving Joe 1 million Bitcoin to buy a Monet. And one of them is going to get screwed out of their painting if the network, depending on which transaction the network decides happened before the other one. So ordering is key. And the question is, how does the network come to an agreement about the order of these transactions? That's a process called consensus. And the challenge here is that in the cryptocurrency networks, nobody trusts anybody else. At my house, we call that Thanksgiving, so you might call that the same thing. The solution to this is to accept proposals for transaction order and reward winning proposals. So there's nodes on the network that are called miners that collect up transactions, they make a block of them, they send them out to the network, and then the network then kind of decides which blocks are the next block on top of the previous block that the network has agreed on. And the way that it incents miners to go collect these transactions into blocks is through a process called mining, where the miner gets a reward for producing a block that the network accepts. To prevent miners from spamming the network with bogus blocks, to make it so that it costs something for them to submit a block, which helps ensure that they're trustworthy, they've got some investment in the network, and also to slow down the rate of block submissions so that consensus can be achieved without lots of different forks, as you'll see. There's a process called proof of work used in Bitcoin, Ethereum, and several other cryptocurrencies. But what miners do is they collect their transactions into blocks. These transactions themselves are part of transaction chains. They put them in the block, and the way that they add their block to the existing blocks is that they have the hash of the previous block in that block that they add. And so now this creates an immutable chain of blocks. If I go mess with block 4561, that invalidates that hash that's in block 4562. Somebody looking at block 4562 will look at block 4561, hash it, and if the hash comes out different than what the hash that's recorded in 4562, they know somebody messed with 4561. So that's the immutability of blockchain through this hashing that happens, this hash chain that gets built as the miners add blocks. So what's this proof of work like? The idea is that in that block header, I've got to make that block header hash to a particular value. And if you think about hashing, hashing is just a random function, basically. And when I can take messages and I can hash them, and each message comes out with something completely different. The goal here with proof of work is I've got to solve a puzzle. I've got to basically come out with a hash that has a certain number of leading zeros in it. And the more leading zeros my hash has to produce, the harder it is to find that number. Because if you take the number space, like if it's just 256 numbers, if I say the leadings, it's got to have, the number's got to be less than 128, I've just cut out half of my hashes are going to be invalid. So basically, I got a 50% chance of solving the puzzle. And you could think if I say that the number has to be less than 8, well, then my random number generator has to try so hard to get a number less than 8. That's proof of work. And you can see an example of this, which is I've got to find a hash that starts with 4 zeros of hello world, the block header, plus I have a number that I can mess with in the block header called a nonce. And that's what miners manipulate is this nonce. They just basically set it at 0, hash. Did I solve the puzzle? No. Set it at 1, hash. No. Did I solve the puzzle? You know, and it goes on and on until they come up with one that solves the puzzle, and then they go, whoop, here's a block. They submit it to the network. The network can very easily verify that they actually solved the puzzle. And if they have, then they add it to the blockchain. Now, the problem is that multiple miners might find blocks at approximately the same time. And that's what happened here, is that we had a blockchain, and then 2 miners solved the puzzle at approximately the same time. So the network, nodes on the network start to get 2 blocks, both valid sets of transactions on top of the previous block. Question is, which one do they mine on? And the answer is, if I get 2 at approximately the same time, I'm going to mine on the first one that I got. And so the network starts to mine and try to create other blocks on top of some fork. And if I get a block now that has other blocks that are deeper than the one I've been mining on, meaning the network's gone ahead and mined 2 blocks when I'm still mining this one down here, the next one down here, then the rule is I've got to accept the longest one, and I've got to discard what I've been doing. So in this case, the miner, if somebody's mining on that left fork, because they got that block first, and then the network, they get from the network 234415 from the other fork, they go, oh crap, I just wasted work on this fork that the network is going to reject. And then they toss that block away, and then they start working on the longest chain. And that's how the network converges over time. So how long should you wait before you consider the forks unlikely? Because the fork can happen in that case of Monet and Van Gogh is if you're looking at the wrong fork and that fork dies, you might just be out of your painting. So the rule of thumb with Bitcoin is wait for anything significant about 60 minutes. The mining time, the difficulty of the puzzles, automatically set by the Bitcoin algorithm to target a block being generated about every 10 minutes. And so after 6, that's a huge amount of mining power that is required to go undo 6 blocks. Like, that's an hour of massive computation. So if somebody wants to go try to screw with the network and undo that Van Gogh transaction that's 6 blocks deep, they've got to overwhelm the network with mining power, something very unlikely. Like I mentioned, the reward for miners is something called Coinbase. So automatically, the Bitcoin network gives miners a reward for getting a valid transaction. And this is the first transaction in a block is this Coinbase that gives them some amount of Bitcoin in reward for them spending this energy. It started out at 50, and it halves every 210,000 blocks. We're down to 12.5 Bitcoin that a miner gets. So it's roughly every 3 to 4 years this go down. You can see that the Coinbase is going to go to 0 sometime out past 2030. And so miners also are incented to mine blocks because they get transaction fees. Now, what are transaction fees? There's no hard-coded transaction fees in Bitcoin. They're simply transactions that don't spend all of the Bitcoin that is in their input. So if I'm giving Alice 10 Bitcoin, I might reference a Bitcoin transaction, earlier one, that gives me 12. If I give Alice 10, and I don't say who's getting the remaining 2, it automatically goes to the miner. And the reason I might want to do that is that miners, they like money. And so they will take my transaction along with the other ones and go, oh, look, this one, if I mine this one, I get 2 Bitcoin. These others, I get less than that. So let me go and put this in the next block I'm going to mine. And there's a fixed number of blocks have a fixed maximum size. They can support 1,000, 2,000 transactions. So if I want to get my transaction in sooner than later, I might increase the fee that I have in that transaction. So let me take a quick look at blocks. And you kind of saw a preview of this here. These are the latest blocks in Bitcoin. And if I click on this, you can see the block. You can see the number of transactions in this one, 635. You can see the output totals of the transactions, the estimated transaction volume, the transaction fee. So the miner got 0.5 Bitcoin on top of the 12.5. So they got roughly 13 Bitcoin from mining this block. And then you can see this is a mining pool. We'll come back to that in a minute. You can see the difficulty. That is the number of leading zeros, basically, that they've got to solve in their cryptographic puzzle. And here's the nonce. Here's what they took the hash of all the transactions in that block. They messed with this value. They came up with this to solve that puzzle to satisfy that difficulty. And there's the block reward. And here's all the transactions in it. And this first one is this Coinbase transaction, plus the mining fees, so roughly 14. So that's a quick look at blocks. All right, so mining, just a quick stop on mining. So I normally don't show photos of my basement, but I thought you'd appreciate this one. All right, no, I'm just kidding, obviously. There's no way I'd allow that rat's nest of cables without ties and proper labeling in my basement. This is my basement. I'm just kidding. These are mining operations. Mining operations that happen to be in China. And you can see the kind of massive electricity that's being thrown at this problem of trying to mine blocks. In fact, people are saying that this is a huge problem for the environment. Well, just how big of a problem for the environment? Here's the site that you can go to that tracks how much energy estimated is being consumed by miners trying to mine blocks. And that vertical axis is terawatts per year. And you can see we're about 73 terawatt per year right now. I put that in perspective. Anybody here from Austria? So this 73 terawatts is about the same amount of energy that Austria consumes every year. And this number keeps growing. And there's a lot of controversy. I'm not going to get into the defenses that people have of this amount of energy spent on Bitcoin and other cryptocurrencies, but that's how much energy it's using. Now, there's this problem called 51% attack. I talked before about having to wait a certain amount of time before you trust a block. And that is if somebody has so much mining power, more than 50% of the network's mining power, they can theoretically mine off their own chain, and they will create longer chains eventually, sooner or later, just through statistics, than the rest of the network. And that gives them the power to go undo things and do double spends. And there have actually been cryptocurrencies that are smaller than Bitcoin that have been hit by double spending attacks. Because the smaller the network, the easier it is for somebody to come along, spend a bunch of money to accumulate power, mining power, and overwhelm the rest of the network and do a double spend attack on it. So this is a real threat. And when it comes to where mining is concentrated, you can go to any Bitcoin stats site and see this breakdown of miners. Mining pools are formed where people give money into the pool buys hardware, and then the hardware goes and tries to find a block. If a block is found, then the rewards are spent out relative to the amount of money that you put into the pool. So if you're a 1% owner of a pool, you get 1% basically of that 13 Bitcoin that was mined if your pool mined that Bitcoin. And so this is a way for people to aggregate their money, get economies of scale in mining power. And so you can see most of the network now is dominated by these massive mining pools. Now, where are these mining pools located? Yeah, and there's that other green one is in Czech Republic. So this is where China obviously has more than 50% of the hash power in the world. Ironically, the Chinese regulators have said cryptocurrency is illegal in China, and all you miners have to get out. So I've just checked recently, and basically they're all like, okay, yeah, whatever. And I don't know what they'll do, maybe take the legal front offshore and leave the mining happening in China. I don't know what kind of workarounds they might find, or just get a giant tanker ship and ship their mining rig off to someplace else. But this is the kind of interesting thing that people are watching right now, given all that concentrated mining power. So that's a look at Bitcoin's cryptocurrency. There's about 10,000 full Bitcoin nodes, meaning nodes that pull down the whole database, which is now hundreds of gigabytes in size, and keep track of the transactions. That example of that website's one of those full nodes. They obviously keeping track of all the transactions that come so that they can show you those cool stats. You can start your own full Bitcoin node. Just launch the Bitcoin software. It's open source. There's different versions of it. Join it to the network. It'll pull down over a few days the entire Bitcoin blockchain, and then you can start messing with those statistics yourself. You can even go create your own miner as well. And that's what a lot of people do with their home basements. I see people get water-cooled rigs and see if they can mine some Bitcoin. What they fail to recognize is that they're paying the electricity bill for that rig as well as the rig. But that's the way it works. And anybody, you don't have to have a full node or anything to get Bitcoin. There's a bunch of coin exchanges. You can go take real US money and buy Bitcoin like I did. And then at that point, you can use the exchange, go there and do Bitcoin transactions through them and get a wallet that you can carry on your iPhone. And there's a bunch of other cryptocurrencies. Anybody invested in any of these? Raise your hand. Litecoin, a few people. Ripple, XRP. So XRP is a controversial one. It's not really decentralized. It's managed by this company called Ripple that is really interested in cross-border payment systems. They just happen to have a cryptocurrency that they use to fuel that. Basically, parties have to pay XRP to initiate these cross-border payments. But they are in full control of the issuance of this currency, just like a fiat currency, what a government is. And so at some point, back when it was peaked, it's also tanked like everything else. It put them among the world's richest people. The amount of XRP they'd issued to themselves was about $60 billion worth at one point. So that one has some controversy associated with it. And then there's Ethereum. How many people own Ether? So a few of you. And there's been a bunch of others. There's been thousands of what are called initial coin offerings, where companies come and instead of doing VC fundraising, they issue a coin. They do an ICO, and then people can buy into the coin. Basically, you're kind of buying into the company. And that coin may be, or maybe not, related at all to what the company does. But you can see that there's just been an incredible run on scams of ICOs, people pumping and dumping these ICOs all over. Anybody been caught by one of these? Just out of, okay, you're not going to admit it. Oh, one person. Thank you for being honest, sir. How many people watch Silicon Valley? So if you haven't watched it, can we roll this? Oh, maybe I have to do it.
I'm Emily Chang, and this is Bloomberg Technology. Decentralized internet company Pied Piper is the most recent Valley startup to ICO. And joining us to discuss, Chief Systems Architect Bertram Guilfoyle. Welcome, Bertram.
It's Guilfoyle.
Okay, then, Guilfoyle. Tell me a little bit about your past experience with cryptocurrency.
Well, I've been mining coins since 2009. It was a different scene then, underground, only true believers.
So I imagine when it came to launching Pied Piper coin that you were the team's head cheerleader. Let me rephrase that. What attracted you personally to an ICO?
What attracted me was the passage an ICO offers across the river Styx of venture capital. What attracted me was an informed disdain for traditional fiat currency, its paper, stained with the greasy fingerprints of your banks and your mints. What attracted me was cryptocurrency's fundamental anonymity that shields private transactions from the peering green eyes of the all-knowing governmental overlords. Does that answer your question?
You have a rather bleak view of financial institutions that have worked for centuries.
Worked? How so?
Thank you, Bertram.
It's Guilfoyle.
Still to come, the aftermath of Hooley's manufacturing
So that kind of summarizes the philosophy of some people that are into cryptocurrency. Now I'm going to switch to talking about something that's based off of blockchain, but not cryptocurrency. It's smart contracts, and it's really the foundation for the enterprise scenarios that I'll talk about in a little bit. Basically, smart contract, at some point, people started to realize that using the simple language that Bitcoin script has in it, that they could start to put business rules in it, like pay this only to this person if this other person has also signed the transaction. And people started to actually create complicated apps on top of it, but it was very awkward because the script was not really designed for that. So there were several other blockchains that came out that had this fundamental concept of an app that could be run on the blockchain. And what does it mean to have an app run on the blockchain? Well, the code and the state of the app are stored as transactions in the blockchain. They can hold themselves. They've got their own accounts, so they can hold money. And they can use that money to execute transactions with other accounts or other blockchains or send money to people. They're immutable, just like transactions for the cryptocurrency transactions I've talked about, because they're sitting as transactions in the blockchain. Function calls to the smart contract are also encoded as transactions with the input parameters and the function name in the transaction. They're publicly readable, so anybody can go look at one of these things. They're bytecode, because all of these run with basically virtual machines that implement bytecode, but you can reverse bytecode into source code and reverse what the smart contracts are doing. They're deterministic, because all the miners execute the smart contract function calls to make sure that they're legal before they say, yeah, this transaction can go into the blockchain, because some of those function calls can refer to state that was generated by previous transactions. And like I said, every call is executed. And to prevent people from DOSing the network, what you've got to do is estimate about how much gas, and gas is like the units of computation that a smart contract will consume. It's how the miners measure how much computation a smart contract execution takes. You've got to estimate about how much that is, translate the gas price to Ether in the case of Ethereum, and then when you send a transaction, a function call transaction in, you give a certain amount of Ether to that. And then the smart contracts execute and the miners rebate you the amount of Ether that wasn't consumed by the execution of your smart contract function call. But that's where gas comes in, and that's why Ether is a key part of it. Now, the most famous smart contract in the world is something called CryptoKitties. Anybody familiar with this one? So a few people. Anybody own a CryptoKitty? So this, you can go to cryptokitties.com. This is built on top of the Ethereum blockchain. It's a smart contract that takes kitten genes, kittens that are defined by a set of attributes, like genes, and the smart contract mates them together, two kitten genes, sets of genes, and then produces another kitten. And so this is kind of the random generation of kittens. And then based off of the genes, you can look at a picture of the kitten. And people really want pretty kittens with good genes, enough that there's about over 200,000 people have bought these things. Somebody's even spent $100,000 on what's considered one of the designer kittens that has really great genes. So this is something that really got out of control. It's under more control now, but this still exists, and you can still go buy CryptoKitties. They're more trying to pivot and focus on charity giving, where they will sell these CryptoKitties at auctions now to raise money. But that is one of the most famous ones, and you can actually go to the Ethereum blockchain and see the CryptoKitty contract, and you can see all the transactions against the CryptoKitty contract, because like I said, it's all out in the open. Now, smart contracts, business logic that you put in the blockchain, a function, where are the places that we're seeing interest in this? Basically everywhere, and this is just some of the examples that we've seen. Trade finance, of course, using blockchain with smart contracts to do cross-border payments and settlement across without having to worry about intermediaries, where the logic of defaults and everything else is encoded right inside the code. Digital music rights, so tracking who gets paid what. Diamond tracing, so something called track and trace, where you say this is a diamond that initiated in a a mine that's friendly to labor, and then that's how I know that I bought something that is not a blood diamond. Real estate, so you can imagine a smart contract that says, I've got a state, the smart contract has some state, which is houses ready to be sold. And to get to that state, you've got to have the inspector fire a transaction, call a function, fire a transaction into the smart contract that says inspector signs off. Another one that says escrow has been paid, and so on. And then once those sets of conditions have been met, the smart contract says, okay, my state's now, house is ready to be sold. And so now you've just gotten rid of all the intermediaries and paperwork required to keep track of these things. It's visible for everybody to see. And so that's an example there. Supply chain management, keeping track of who has what across a distributed network of parties that are moving something along. I'll talk more about that one a little bit, and the list goes on and on. And there's not just Ethereum as a smart contract-based ledger. There's other ones like R3 Corda, Hyperledger Fabric, Ethereum, which I mentioned, Quorum, and Ripple itself. These are all smart contract blockchains that are really, their fundamental purpose isn't cryptocurrency, it is business processes on top of blockchains. Let's take a quick look at Ethereum smart contracts. And for this, I'm going to switch to Visual Studio Code here and show you a smart contract. This is in the Ethereum language, Solidity. So these files have SOL, and there's actually a Visual Studio Code plugin that understands Solidity syntax. And that's what I'm looking at, this refrigeration transportation smart contract, which is going to track an item and make sure that it doesn't fall out of health safety guidelines, humidity and temperature. And you can see this initialization sets, you can call this constructor and say, this particular item, refrigerator transport item, its maximum temperature is this, its minimum temperature is that, so on. And then smart transactions can be fired into it that report the current humidity and temperature, along with a timestamp. And then that's recorded in the smart contract. So you can also query the state and say, okay, when's the last telemetry that this thing got? What was the temperature? And then finally, you can also transfer responsibility. This would be as one shipper's giving it to another one. They can assign now this item to the other shipper. That's recorded as a transaction, so anybody else can look in the blockchain and see it. And now that shipper, the one that's been given to, can go and call that ingest function. Only the owner of it can call that ingest function. And what I'm going to do is deploy this to the Ethereum test network. And to do that, I'm going to unlock some Ethereum. There's an Ethereum test network that is basically free to use. So this is where you can experiment. It's public, just like the main Ethereum network, or mainnet. And it's got its own concept of Ether. Oops. Personal, unlock. I'm used to typing ETH0 for Linux, by the way. And so what I can do is now compile. And so what this is doing is compiling that smart contract, creating a transaction that includes that smart contract bytecode in it, and submitting it to the Ethereum Ropsten network, this test network. And what we're going to get back is the address of that smart contract and network, which is the hash of the transaction that's its initial creation. And now when I want to fire transactions or call functions into that smart contract, I simply reference that smart contract address with a function call, which is represented, again, with some bytecode that says, this is the function, these are the inputs. So what I'm going to do after this is done is run a little script here called tx negative, which is going to, here, set the thing out of compliance by sending in, calling this ingest telemetry function that we saw with a value that exceeds the initial value that I had set for this. So this is deploying. We're going to get the smart contract address here in a second, and then what we can do is actually go see that in the Ropsten network. It's taking a little bit longer than normal. Okay. Give it another second, and then what I'll do is I'll come back to it and move on. Okay, let me come back to that in a second, because that will surely finish in another, oh, there it goes. And so here's the smart contract address right here. And so if I go to the, whoops, Ropsten Network Explorer, which lets us view that should have okay, I'm not sure what, oh, there it is. It just showed up. Let me see. Here it is. So this is the transaction that's put our smart contract. You can see smart contract creation right here, and you can see the transaction hash. If I click on that, this is the smart contract bytecode that we just submitted to the Ropsten network. And now that we've got that there, we can then execute functions against it, like I'm going to do, like I mentioned, this changing the state of that contract. I'm going to use a different Ropsten account to do that. Okay, accounts. And by the way, up key doesn't work well in this thing. You can see that it doesn't really work at all. All right. And now what I can do is go back to Visual Studio Code, and I can say truffle, which is the dev environment, tx negative .js network ropsten. And then what's going to come back here after a second is that's firing that, calling that ingest network thing. And then this is also going to call a function that checks the compliance status. And you're going to see that this is going to come back as this thing is out of compliance. Now that it's exceeded, that I fired a transaction in there that says this refrigerated item has exceeded the humidity. Because I sent in a 60, its max is set to 50. So now you can see compliance status is false. So that's an example of a real world kind of contract being executed on a real Ethereum blockchain. So speaking of Ethereum blockchains, I've been showing you public Ethereum there and public Bitcoin. But what's coming now for enterprises are private blockchains, ones where they're not public, only certain parties can participate in them. And this is typical consortium architecture that we see. You can see the blockchains at the very bottom, or the ledger. You have identity and key management. You've got these users that don't want to manage those raw keys to sign things. They actually want to put them in key management, hierarchical key server management servers like Azure Key Vault, and they want to use real identities to unlock those keys, like ones provisioned through Azure Active Directory. They've got a consortium governance on top, which is who can be part of this network. What rules do they have to abide by? What is the software that they need to run to be part of this? And then you have apps that run on top of this that allow them to do the smart contracty things. Now, one of the benefits you get out of being in these consortiums is you don't need to do proof of work. If you take a look at consensus algorithms, they're really along a spectrum. So even the Ethereum public network, its transaction latency is 10 seconds rather than 10 minutes, but it's still long because nobody trusts anybody in public networks. But in a confidential or a private network, you can use other algorithms like Byzantine fault tolerance, which operate at much smaller scale. They can give you better performance, even when people don't trust each other. Proof of stake, which now is there's attempts to be introduced that into public networks, but that can work in private networks. The one that's most commonly used in consortium networks is proof of authority, which says these are the participants that can vote and say that these are valid transactions and valid blocks. We trust them all. The network trusts these particular entities. And then you can also do fault-tolerant consensus. This one requires everybody to really trust each other, which is everybody's going to behave appropriately, which is normally not the case even in consortium blockchains. So this one you rarely see. Now, we've had lots of different scenarios where we partnered with customers on consortium blockchains, and you can see just a list of them here of some of the key ones that we've talked about publicly. And I'm going to just talk about 3 of them just to give you an example of what we're seeing customers doing with these consortium blockchains, starting with Maersk. So Maersk is a shipping company. Obviously, probably everybody in here has seen a Maersk ship or Maersk containers. They operate hundreds of ships around the world, one of the largest container shippers. And they've partnered with us and with Ernst & Young, with Willis Towers Watson, and several other insurance companies, and Guard Time, ISV, Insurance ISV, to create a network called InsureWave. The idea here, and the reason that Maersk was motivated to do this, is that their ships pass through different kinds of waters, and they buy insurance for those ships from a variety of insurance companies. Depending on which part of the world they're in, they might get better rates from one insurance company than another, and depending on which kind of items they've got on the ship as well. Well, the challenges that they've run into are, as they're moving between waters, or moving between insurance companies, or moving into waters that require different policies, like they're moving into a war zone, their ship requires more insurance, is disputes as to, okay, which policy was effective when? How much money does Maersk owe in the insurance companies? What are the liabilities that the insurance company owes Maersk? And some of these disputes, which don't come up that often, but when they come up, they cost a lot of money and a lot of time for everybody involved. So what Maersk is doing is putting this on a blockchain. So when the ship moves into water, that's war zone water, it fires a transaction into the smart contract that's tracking that ship. That causes the insurance policy to kick in at that point by connecting that to an external business system that says, new insurance rates gone up, start tracking this. And then when it comes out of the water, it goes back down. It fires another transaction saying, okay, remove that policy or lower the liability on that policy. And that's being done by humans right now on the ships, or people tracking the ships. What they're going to be doing is wiring the ships to GPS and the blockchain so that these things fire automatically. No humans involved. It's automated. As the ship moves around, the insurance is being tracked automatically. So that's an example there. Another one is one that we did ourselves with some partners, including Electronic Arts, on making sure that artists that produce artifacts for games and the publishers of those games get their royalties paid in a timely manner. And right now, with existing kind of royalty payment systems, I don't know if anybody in here has ever published something where you're owed a royalty, but so having been a book author, it's still done by paper. I get it like 3 months or 4 months later. There's no way for me to know if they're telling me what's really I'm owed. With this kind of system put on a blockchain, well, actually in the game publishing business, it's roughly 45 to 60 days before the publisher gets paid for a sale of an item, like one of the game titles. It's another 75 days before the artist gets paid by the publisher. So to shorten all that and to give people real-time visibility into what they're owed and how their title is doing, putting this on blockchain, these sales on blockchain. So all the participating publishers and artists that want to be part of this, and there's already a bunch signed up, now have real-time visibility into how many items are sold on which days, knowing exactly how much they're owed because of that, and they can get their payments more quickly, and there's fewer disputes because it's all out there in the open for them to all see it. And the third one that I want to highlight is Webjet. This one is, this company is a hotel company that does travel bookings, and they also own some hotel chains based out of Australia. And the travel business is one of those very decentralized businesses where hotel inventory changes hands, sometimes as much as 5 times, going from the hotel saying, I've got a room, to somebody buying that room through travel agents and brokers and other intermediaries. And each one has their own database. And so what happens is that somebody thinks a room's available. It's really not available anymore because it's already been sold, or that room gets lost. Nobody, in transacting it between one party and another, it gets dropped. And so, this leads to a ton of waste, a ton of fraud. There's about $10 billion per year in fraud and waste in the travel business through these kinds of problems. And so what Webjet's created is this blockchain network called ResChain. And ResChain is where they track these transactions among all of the travel agents and the hotel suppliers and the other parties as part of this. They've already reduced the number of disputed transactions by 90% since putting this into production just a few months ago. So that's an example of blockchain. Nobody really wants to trust anybody else running this centralized thing, and blockchain can come and give that decentralization and visibility. One of the things I want to mention is that there's, like I said, I showed you earlier, there's tons of other examples of these blockchains in production or going to production, like 3M, food safety. 3M has got one for pharmaceutical authenticity, where they've got their tamper-proof containers. Pharmaceuticals get bottled in those. They can be checked for authenticity and that they haven't been tampered with. And then that goes through a supply chain all the way out to, for example, a pharmacy, and by tracking that on a blockchain with IoT that is going and saying a link step of the way, has this, checking to make sure this thing hasn't been tampered with, that you can verify that the drug that you get at the pharmacy is actually the legitimate drug produced by a factory. So we've got a bunch of blockchain initiatives at Microsoft that I mentioned I was going to wrap up with. One of them is blockchains in the marketplace. So we have templates, Azure Resource Manager templates, that you can go into the marketplace. There's roughly 12 or 13 of them for roughly 4 or 5 or 6 different ledger types, where you can go and within a few minutes deploy a single node for your own dev test of a blockchain, a multi-node for a larger proof of concept, or a multi-member one that you might want to even put into production, where you're collaborating with other parties. So the templates support all of these kinds of scenarios, including Ethereum network, for example, that you can stand up nodes in different Azure regions for high availability. So it's a quick way to get started just with the core of a blockchain. But one of the things that we've seen as we've been working with customers is that this kind of stuff, managing this low-level stuff, is very complicated. Setting up the blockchain network, and then if that's taken care of for you by the template, the next level up is like, how do I wire this up with Azure Key Vault? How do I get Azure Active Directory to manage those keys? How do I look at this in a SQL database, the history of these transactions? How do I kick off a workflow to my CRM database, for example, if it's blockchain needs to kick off something there? How do I do all that? And how do I create APIs and front ends and authentication for people to be able to interact with the blockchain? All of that is left as an exercise to the reader until we develop this, which aims at taking all that stuff and making it go away. It's called Azure Blockchain Workbench, and we auto-generate a blockchain application platform for you when you go create one. You can go create one of these in a few minutes. Underneath the hood, you're getting an Azure database, you're getting a web front end, an Azure App Service, you're getting business logic on Azure App Service, you're getting Xamarin apps that are automatically generated with interfaces to interact with the blockchain. You're getting Azure Active Directory stood up and connected with identities and keys stored in Key Vault. And you're getting a web interface where an administrator or somebody interacting with the application can go and see what's going on and execute transactions, but not knowing that they're executing transactions, basically just setting properties on a smart contract. And what happens underneath the hood is keys fetched out of Azure Active Directory, Azure Key Vault, transactions created, transactions fired in the blockchain, and that's just all invisible underneath. And we started by releasing Ethereum, but we're going to be releasing other support for other ledgers coming up. So I'm going to show you a quick demo of this. Now, if you saw us standing up here right before the presentation, it was because I wanted to show you that track and trace example with an IoT device here. And it's not working, is what signal I got. And that is because there's something wrong with the IoT device. So I'll just show you this in the UX. So here I've got the refrigerated transport. So let me show you how you create one of these things. It's pretty straightforward. I want to create a new application. Oh, sorry. I want to create a new application here. So this is the blockchain workbench. I've created an instance for myself, and I've got a bunch of applications already deployed, but I want to create a new one. So I upload the contract configuration, and then I upload, oh, great. Okay, where was I? And this is a piece of metadata that you create. Oh, I can't. Wanted to look at this in Notepad, but all that is a little piece of metadata that goes along with that Solidity contract, which is the one we just looked at. This is the exact same thing that we just looked at. Okay, ignore. And I want to deploy this. So it takes about a half an hour to set up that metadata. Take that smart contract, which has this state information. Blockchain Workbench looks at that metadata, looks at the smart contract, and automatically produces the web UX, the application clients, like I mentioned, for mobile devices. And now I didn't mean to deploy that, but it's deploying. But here's an existing one that I've deployed, and I'm going to create a new contract on it. I just should have waited. The network is laggy. So I pressed the new contract button. I'm getting a lag. What this new contract button is going to do is create an instance of that smart contract, refrigerated smart contract, that I would do when I'm creating, shipping a new item. As soon as this responds. Okay. Oh, I have no idea what's going on with this network today. But, all right, well, I'm going to move on and come back to that and see if it suddenly starts listening to me by talking about one more thing that we're doing, which is taking a look at how we can better help blockchains work in the enterprise. Now, what I have talked about so far are the basics of blockchains, and there's some limitations with the public blockchains, like the low performance that they get. The low performance that they get because they're using proof of work. Even proof of authority is relatively low performance when compared to something like just quorum-based Paxos algorithms, where you trust the parties to all be operating, because then you only have to basically have one of them validate what's going on. There's lack of flexible confidentiality, and this is perhaps the biggest problem with enterprise blockchains. That supplier scenario that I told you about earlier, item moving through a supply chain, lots of suppliers being there. One of the challenges with that is that if you've got something where you don't want different suppliers to see what's going on with different kinds of shipments moving throughout the network, or you've got finance where you don't want the parties to see the fact that there was even a transaction between these two parties, much less the value of that transaction, then you've got to do some kind of gyrations to try to obfuscate what's going on. And there's a few efforts that you can see going on in blockchains to try to address the confidentiality problem. One of them is called private transactions, where if I want to send some money or some asset from me to somebody else, I can encrypt that transaction so that only they can see it. The rest of the network just sees the encrypted transaction. But they, with their key, can decrypt it and see it. And then they can know that I've given them that item. There's some challenges with that, though, because once I've given somebody something like that, they can't really give it to somebody else without revealing some information about the fact that they got it from me, because everybody would say, do you really own that? Prove to me that you really own that. So there's something else that's being developed called zero-knowledge proofs, which is a cryptographic way to tell somebody something, prove to somebody something without revealing any other information. So in that example I just gave you, if you use zero-knowledge proofs, I'd be able to say, I prove to you that I got this money and it's through valid means on the network, but I don't have to tell you who I got it from. And you trust that assertion based off the cryptography. And that's very complicated cryptography. It's very slow as well, and it's really hard to apply to general cases. But there's been a tremendous amount of research into trying to make that more flexible and a more higher performance. But nevertheless, it's very, very complicated and rigid. So we've been working on something called Confidential Consortium Framework for Enterprise Blockchain, which is allowing you to create a trusted network based off of trusted execution environments. Remember I talked about these black boxes. You can trust the code inside them. You trust the provider, like Intel SGX, that creates that black box. And that means that if I have an algorithm, and some data, I could have you run it on your computer, knowing that you're not going to be able to mess with it or see that data, because Intel SGX is going to keep you away from that data and away from that tampering with that code. And the way that I know that I can trust it is I get an assertion from SGX, your computer, that says, I am an SGX processor. This is the code that I'm protecting. And now I can say, OK, that's the code that I trust. I can establish a secure connection with it and give it keys to decrypt data. And you can think of this confidential networking as just the computers doing it among themselves. Are you running code that I trust? If so, I'm going to release keys to you. And now we all have the keys. We can all do these transactions. And now once you got this, you can do low latency performance and very high transaction throughput. Because all the nodes trust each other, you can do that fault-tolerant consensus algorithm, the one that as basically any distributed system executes. And I want to show you this in action. Cocoa framework is actually going to be released in open source by the end of the year. And it's going to support initially Ethereum. And I'm going to show you. So this is implementing 1 million Ethereum transactions, Ether transactions, on a private blockchain network of 15 nodes. And what this is going to do is show us the transaction throughput. The transaction throughput on the public Ethereum network is roughly 10 transactions per second. But with this, what we're going to see is something much higher than that. And you can see that it's about over 6,000 transactions per second. So this is like more like real database kind of throughput. Now to show you there's overhead of Ethereum itself, we've created a very simple Bitcoin type of protocol. And this will show you kind of how fast Coco can just do regular, or the Consortium blockchain framework can do regular transactions. The other aspect about this is that you can implement arbitrary confidentiality models on top of this, because you trust the code in that enclave. So you can say, enclave, only show transactions to these people, these transactions to these people. Like, for example, only show those supply chain transactions to the originator and the target, nobody else. Or the retailer can see them all. Or in a financial system, only participants in the transaction can see the contents of the transaction or even see that they happened, but the auditor could see them all. So all of these confidentiality models are very simple to implement because it's just like implementing access control on a standard enterprise workload. And you can see right there that we hit 60,000, close to 60,000 transactions per second. So that's across 15 nodes, and we're going to be driving this up to 100, 500 nodes, and expect this to get up into the several 100,000 transactions per second when we're all said and done. So we're aggressively going after this. And this will be open source. You can deploy it in Azure confidential computing virtual machines. You can also deploy it on any of the Intel SGX-enabled hardware you've got on premises. We expect customers to build these networks, trusted networks, on their own, in other clouds even, and with nodes in Azure. So that's a quick look at some of the things that we're doing with blockchain. So with that, I want to go ahead and wrap it up here by just giving you the summary here of the things that I've talked about and going back to this question, because really this is where it's all at. If you're at a company and you're looking at blockchain, you got to ask yourself, do you have a scenario where there's multiple participants, want to interact, none of them among them is trusted to operate the database, and they don't even want to outsource the operation of the database? If the answer is no to either of those, or to both of those, then it's probably not a good blockchain scenario where you can solve the problem much more simply with traditional centralized database approach. So with that, I want to conclude. I want to say that if you're invested in Bitcoin, how many of you own Bitcoin? Okay, hold on to it. It's supposed to go back up. That's what everybody's saying these days. In fact, somebody just came out yesterday, some analyst, and said Bitcoin is going to skyrocket soon. So, and for everybody else, do not buy it. All right, with that, thank you very much. Hope you had a great Ignite.